Galvanic and electrolytic cells require a bit of understanding of redox chemistry, so that's where we're going to start. And by the end of this video, you'll be able to write your own summary page, just like this. So this will be the video content. I know it looks like a lot, but it'll be fine. They're like 2 slides each. So, let's say you've got a metal and another metal. And as you know, metals have delocalized electrons. So how do you get them to move? Well, you immerse them in a solution of their respective ions of 1 mole. Then you connect a wire between them. And there should also be a porous membrane here, so there's a continuous potential. And then the electron transfer will occur. Now, you're probably thinking, well, it can't just be that simple. You can't just get any 2 random metals, immerse them in 1 mole of their solution of respective ions and get electrons flowing, and you're right, there are a lot of rules that we need to go through before we can fully understand this cell. But this is the basic idea. So let's have a look at the general formula for reduction and oxidation of metals first. So this equation for the rest of the video is going to represent the phenomenon of a metal atom losing electrons, and which, as you should know, that is oxidation. And this equation will represent the phenomenon of a metal atom gaining electrons, which will be reduction. Alright, so what's the overall cell potential under standard conditions? So this is just the reduction potential minus the oxidation potential. So that is pretty much it. And you get your potentials from a table, so don't worry, you don't have to make a cell during your exam. They give you a table with the numbers. Alright, the standard EMF series table, the one that I was just talking about. So we're going to refer to this one. There's a lot of tables that have a lot of different elements in them, but we're going to refer to this one. So it's okay if yours looks different. So this is the electrode reaction. So you could have gold as your electrode, you could have silver as your electrode, you could have iron, whatever, anything on here. And this is the standard reduction electrode potential. So that is the reaction which occurs, and this is the voltage which is generated when this reaction occurs. And just don't let that word electrode scare you. All it means is just a metal. They're just calling it an electrode because in this context we're extracting electrons from it. It's still a metal. We're just calling it an electrode. Alright, so how do we find reduction and oxidation potentials? So to find the oxidation and electrode potential, change the sign and write the electrode reaction backwards. So if you wanted, this is just the reduction, say reduction electrode potential for potassium is negative 2.924. But if you wanted the oxidation one, you just switch the sign around and you write the equation the other way around, and that's it. It's not that bad. So this is these are just for the standard conditions only. So what is the standard condition? I've been mentioning it a lot. So in order to measure the relative activity of electrodes and metals, we need to take them relative to the hydrogen electrode, or that's what scientists decide to do. So all those voltages you see, they're relative to the hydrogen electrode. If you see here, hydrogen is 0, because hydrogen to hydrogen is just 0. And each electrode is immersed in 1 mole of its respective ions. All reactions occur at 1 atmospheric pressure, and all reactions are at 298 Kelvin, 0.15 if you must know. So so this is just for standard equation. It's just V2 minus V1, which is the reduction potential minus the oxidation potential. But what happens when any of these standard conditions change? So what happens when the molarity changes, the temperature, the number of electrons, what's going on? So the reduction and oxidation potential are still the standard conditions, but we adjust their actual voltages depending on the change conditions shown here. So you just check this. The standard condition is still important, but we can manipulate these standard conditions to show what the conditions are when we're conducting this experiment. So R is the gas constant, N is the number of electrons participating in either of the half cell reactions, F is the Faraday constant, which is just how much charge is contained per mole of electrons at 25 degrees Celsius. Alright, so it would be helpful to memorize this equation, so let's memorize it. So how do you remember this part? Because I don't like looking at the formula sheet at all. So the reason why we just remember V2, this is your reduction, this is your oxidation, and how to remember it is that the R looks like it has a 2 hidden inside of it, so you just remember it's always reduction. Can't really go wrong with that. And to remember that V2 is the reduction potential and that it goes first, think of how most equations are in the form of T final minus T initial. So you can think of the 2 as a final and the 1 as the initial. Or a lot of people will say cathode or node or third node, whatever helps, but for me, the 2 hidden inside the R and T final minus T initial is what helps me a lot. So, if you remember that V2 is the reduction potential, then V1 must be the oxidation potential. The negative sign in the equation accounts for the change direction of changing the standard reduction potential to oxidation, so don't worry about doing this yourself. The calculation does it for you. All you need to do is plug in the voltages on the EMF series. That's it. Alright, so this part, I'm sorry I don't have a memory trick, because it's just interesting. I mean, R is 8.31 joules per mole per Kelvin. And you multiply it by Kelvin, and then N is the number of electrons participating in the electron, and then that's Faraday's constant. So, what about this part? What do we do here? So, how do you remember that the concentration of oxidation goes up the top, and the concentration of reduction goes at the bottom? So the way I remember it is that oxidation always seems to be at the end. It's always losing electrons. It's the lowest on the standard, we'll get to that later. It's the lowest on the standard EMF series table. It's the last one to be considered in the cell potential equation. But here, oxidation gets its revenge and comes out on top at the very, very end of electrochemistry. There it is. It wins at the end. That's how I remember it. So I mentioned that oxidation is the lowest in the standard EMF series table. What did I mean? So yes, another useful memory trick is included. So when you're finding out the cell potential using either the standard Nernst or the unstandard Nernst equation, you figure out which equation is the reduction potential and which is the oxidation potential by its position on the reduction table. So in this table, the lower you go, the more anodic and active the elements become oxidative, and the higher you go, the more cathodic and inert the elements become reductive. And you can see how gold is at the top. To remember this, I imagine oxidation falling. Oxidation sounds like, oh no. So I have not forgotten this rule since. So when you have a question that says, okay, you've got nickel and you've got tin, which is the anode, which is the cathode. I know this is the anode because it's oxidation, oh no, it's falling, so it's done. The electrons are going to flow from here to there. And as well, anode is the negative and cathode is the positive terminal. So before continuing, see if you can write down all the tricks you just learnt in your notebook. You don't want to forget it. You don't want to be an hour before your exam, like I am right now, and thinking, okay, I've forgotten most of it. So make sure you write everything down. Make sure is that my alarm? I'm going to assume that the microphone can't hear that, and I'm going to continue. So, summarize everything you have learnt. Go pause the video, give it a go. I'm going to go tell my alarm to be quiet. When I come back, I hope you've written something. Alright, I'm back. Let's go. So this is the first thing I wrote, was that by immersing a metal in a solution of its ions and connecting it with another metal, we can encourage a flow of electrons to flow across the wire from one half cell to the other. The half cell which releases electrons is known as the anode, and this is where oxidation occurs. This can be described by the equation for metals undergoing oxidation. So N is the number of electrons that are being released, and as a result, it gives a positive charge to the metal ion. So, the half cell which takes the electrons is known as the cathode, and this is where reduction occurs. So this can be described by this equation, where the number of electrons gained by the ion gives it a neutral charge. Remember, N is important when you go into the Nernst equations, how many electrons are being exchanged. So if an electrochemical cell has each of its electrodes immersed in 1 mole solution of its ions, it's under a pressure of 1 atm and of temperature 25 degrees or 298.15 Kelvin, we can use the following equation to calculate cell potential, which is V2 minus V1. So the negative sign accounts for the change in direction relative to the reduction potential listed in the standard EMF series, and V2 is the reduction potential directly from the standard EMF series, and V1 is the oxidation electrode potential, also read directly from the standard EMF series. If any of the mentioned standard condition is not present, we use a different equation. So we need to use this one. You can see there's the Nernst equation in here. So where T is the temperature in Kelvin, R is the gas constant, N is the number of electrons participating, F is Faraday's constant, 96500 coulombs per mole, indicates how much charge per mole of electrons are at 25 degrees, and the concentration of each ion solution to each respective electrode are M1 and M2. Remember, M1 is up top. So if we want to find out which half cell is the anode and which is the cathode, we refer to the standard EMF series. But if you're working under non-standard conditions, that general rule of whichever one is the lowest is the anode doesn't hold because the conditions have changed. So if you get a negative answer, that means you have an electrolytic cell and it requires an external power source. But if you get a positive answer, it's a galvanic cell and it happens spontaneously. So the question will usually state, figure which one is the anode or the cathode, or if it doesn't, they usually don't really care about the sign. They just want to know that you understand the non-standard condition equation, but keep that in mind. Alright, and those are all the notes really for the video. That's it. This is everything you've learned, as well as the difference between a galvanic and electrolytic cell, and that's it. Good luck for your exam, and good luck for my exam, but I should be okay with this stuff. Alright, have a great day.